Hello everyone. In this video, we are going to look at the analysis of trusses. By the way, just wanted to let you know that on my channel, I have broken down the playlist I had on basically machine design and statics and solid mechanics into three separate playlists. So now there is a statics playlist that you can see here. And then there is a separate one for machine design and a separate one for solid mechanics. So this video is going to go right into my statics playlist. And one of the videos that I made in the past about trusses was to recognize zero force members. So if you go here and you look, there is one video that I talked about how to locate and what's the meaning of a zero force member. But I did not talk about analysis of trusses in general, so this is what I want to do just for the completeness of that playlist. So what is a truss? Truss is a structural member that you see all over the world for carrying physical loads. Their goal is to carry physical loads, so you can see them in bridges, you can see them in basically under the roofs, right? And in so many places. So if you just say truss in real life, correct? And then you see them in all over the world. So most of the time it's the bridges, but again, under the roofs of many houses also you can see them, but again, the biggest thing is the bridges. Okay, and you can see even something like Eiffel Tower, so many other things, they can kind of be classified as a truss. So the goal of it is to carry load. Okay, so now what does truss analysis means? It means to find the forces inside each member. And then later in solid mechanics, you use them to determine if the truss can tolerate all that load or not, and it's going to break under the load. And it's typically way more than that. But here in statics, the goal is to just find the forces within each member. But really, if you want to analyze a truss, you have to do a lot more. You have to do vibration analysis and so many other things. So here we are just talking about static analysis. And we assume that there will be no real big varying with time displacements in the joints or in the truss. So it's just a static deflection. And again, we don't care about deflection, we only care about forces. Now, before we do that, there are three major assumptions that we have to consider that when we do truss analysis with this, what we call simple two-force member analysis, which is the simplest thing, there are three assumptions that we are making. First thing is we assume that the masses are negligible for the members. Okay, so the members are not heavy, and you might say, well, they are heavy. They are made mostly out of steel or wood or something. They are not really lightweight. Is that a good assumption? When we compare them to the actual load that is on the truss. So if you look at this truss, this external force F that the truss is carrying, right, that should be a lot bigger than the weight of each one of these individual members. Okay, if that's the case, then that is a good assumption. Otherwise, we have to do something about this mg, and I'm gonna talk about it. But first, we assume that the masses of the members are not big compared to the external loads. And then the external loads are only applied at the joints. And what kind of joints we have? The members are assumed to be pinned together. Okay, so we assume that these connections are pins. In real life, these are not pins. They are mostly bolted or welded together. Okay, and the forces are not also always applied at the joints, right? So for instance, if this is a bridge, you know that when a car is coming and basically driving, right? Let's say it's a semi or something, and it's driving there, the load of it is not just applied to that joint right below it, right? It's a distributed load, and you have to do something about that as well. So all of the things we do here, all of these assumptions, they have to be really handled in real life situations. This is just some assumptions to make the analysis simple using a 2 or 3/4 member. And what does 2/4 or 3/4 member mean? Means a member that, if you look at it, so let's say this is a member like this, and on this end of it, and this joint, there are only two forces applied. So if you call them F1 and F2, or T1 and T2, right? So let's say this is T1, this is T2, or F1 and F2. Well, first of all, they have to be equal in magnitude and opposite in direction. Otherwise, this member is not going to be statically, basically at stable or at equilibrium, right? So clearly they have to be equal. And what is the line of action for these two forces? It has to be along this line that connects these joints together. Okay, they have to be along that. Otherwise, if they are not, if like one of them is like this way and the other one is like that, okay, then if you look at any of these joints, there will be a moment and the member should rotate. So it cannot be in static equilibrium. So the forces should be along the line connecting the two joints, and they should be equal. And again, remember, we are neglecting mg. Now, if you cut this member anywhere and look inside of it, you know, based on what you know from solid mechanics, of course, you might say, well, I don't know solid mechanics, I just here to learn statics. But I mean, in general, when you cut any member, there are three reactions that you can see. Okay, a 2D member, when you cut it, there are, so if you look at that location and you cut it and bring it out and look at that one side of the cut, like here, and this is that T. In general, there are three reactions, right? There is a what we call a shear force V. There is this normal force P, and there is this bending moment M. Okay, in 2D and in 3D, of course, there are 6 of them. But here, in general, these are the three forces that you have to determine. Now, in a 2-force member, because there is nothing else on this half other than that T force and no mg, nothing, you can see that V is equal to 0 and M is equal to 0. The only thing that is not 0 is P, and that is equal to T. So if you look at it, it's going to look like this, and that means anywhere you look, there are only 2 forces anywhere on any part of this member, whether it's the entire member or a portion of it, and they are equal and opposite. And in 3D, it can be a 3-force member, right? And by 3-force member, it's really just 2 forces along the member, but they are 3D forces, really. Okay, so, and 3-force member, you might say, well, there could be a third force, but in trusses here, we assume that we are really working with one single force along the member. Now, this force can either make the member be under tension, so the members could be under tension, or it could be under compression. And there are some scenarios where the member has no force on it. So the member has no force, tension, or compression. That is that video I called, and it's called 0-force member. So that member is not carrying any load. Then you might say, why it's there? I recommend you watch that video to see why we should add a member that does not carry any load. But in general, truss members are under tension or compression. Okay, so very fast, let me talk about a couple of things here that are important. One is, we said, if the masses of the members are not negligible, how would you handle that, right? So if this member here, whatever this member is, let's call it member AB. So if this member AB, if you call these joints A and B, if this member has some weight that cannot be neglected compared to F, what would you do? One simple thing they do in statics is they break that mg into 2 parts, equal parts, mg over 2, mg over 2, and they put them over both of these joints and get rid of the one that is along the member. Okay, so the distributed along the 2 joints, assuming that is homogeneous. Otherwise, you have to do it proportional to the or inversely proportional to the distances. Okay, but you can break it down and distribute it among the neighboring joints. Okay, the 2 joints at the 2 ends of that member. So this is one way to handle masses of the members or weights of the members that are not negligible. And the other thing is, if the load is not applied on the joint, again, remember the weight of that car that we had, So if this weight is basically applied over here, then we replace it with an equivalent force. So let's say the equivalent force is right there. And then again, that equivalent force has to be broken down between these joints. So if it's applied to all of this bottom portion, then maybe each one of these joints is taking a portion of it, depending on how close they are to that weight, right? So the closer they are to it, the bigger portion of the weight they are carrying. As I said, inversely proportional to their distances from the joints to that equivalent force. Okay, so you can break it down again in a similar manner. So you can handle these two scenarios. Now, what about the case that they are not pinned together? So as I said, in real life, if I go back and show you that trusses, you can see that in real life, if you look at any truss, let's see if there is a big, this might be good. So if you look here, you can see that these are all basically rivets, right? Or they could be bolts, or sometimes there could be welding. So if that's the case, in older ones, sometimes they use welds, but most of the time they use rivets, which are much better in terms of strength against earthquake and shaking, because welds are very susceptible to it. But in reality, you never see the members being pinned together. They are always these brackets, and they are kind of pivoted. There are rivets, and there is not one, there are several. So it's completely, you cannot really say that's a pin, because a pin should allow a rotation, and there is no rotation anywhere here. So if that's the case, then you have to analyze what we call the machines, okay? And that is one of my future videos. So in that case, then we cannot just, whenever we cut, we cannot just replace that cross section with a single axial force. We have to also bring in the shear force and the bending moment, and that makes analysis of those machines a little bit harder, because now you're dealing with three unknowns at each section. But we'll talk about that. So this one is completely assumed. We assume that we observe that. Okay, now moving on, here we can look at trusses either in 2D or 3D. So a 2D truss is all fit on one plane, and 3D is what you see in this power transmission towers, or something like the Eiffel Tower or so on. You see these in those structures. These are, you mostly see in bridges and under the roofs and so on, right? Or under the balconies, stuff like that. So we're going to look at them separately. In 2D trusses, which are a little bit simpler, if we show the number of members of the truss, these guys, with M, and the number of joints with J, then for 2D trusses, the number of members and joints should be related to each other by this simple formula, that M equals 2J minus 3. Well, let's look at this one, for instance. Here, how many members we have? We have, and remember that this whole thing, from, if I give them some name, this is A, this is B, this is C. This is not one member. It's not one member AC. It's A, B, and BC, okay? So the members are only, remember, they are only pivoted, but they are pivoted only at the ends. The members cannot be pivoted in the middle. If they are, then that means that there is some pivot load somewhere in the middle, but the load should only be at the ends. So members are only pinned at the ends. So here we have member AB and member BC. Remember that. So that's 1, 2, 3, 4, 5, 6, and 7. So in this case, this M is 7. And how many joints you have? You can see that there are 3 here and there are 2 there. So you have 5. Is that work? Yes. 10 minus 3 is 7. So you see that it is working. And if you look at another example, let's look at this one, for instance. Is that also following the same thing? So here, if you look, you have 3, right? And then another 3, 6. So we have 6 along the triangles. And then we have 4 here on this square. So J here is equal to 10. And if we look at the number of members, right? So here we have 1, 2, 3, 4, correct? And then 5 and 6, and then 7 and 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Is that working? Remember, m should be 2j minus 3. 2 times 10, 20, minus 3, 17. So you see, it is absolutely what? It is absolutely working. Now, you might say, can I add some other member? Like, for instance, can I add another member like here? Something like that. Can I add that? You can, but then if you call this a pivot here, let me add a color. If you call that point a pivot, then you have this member and this member. You cannot say that whole thing is one member anymore. So by doing that, what did you do? You added one extra member, so you made the number of members 8. 2 actually, because you made that member in 2. You added one more, so you made this 9. I'm sorry. And then how many more joints you have added? You have added one extra joint. Would that work? So 2 times 6, 12 minus 3, that's 9. You see, it is working. Okay, so you can, yes, you can add one extra member here to reinforce that. And why would you do that? The reason is to reduce the length of this member and make it shorter, because shorter members can withstand buckling a lot better. If you don't know what buckling is, I have done buckling analysis under my SolidWorks, but I don't think under my solid mechanics playlist I have a video separately on buckling, because it's under development. So yes, one of my future videos I talk more about buckling, which is the lateral bending of members. And the shorter the member is, the stronger it is going to be against buckling. Like if you make a member 2 times shorter, it is going to be 4 times more force needed to buckle it, which means laterally bending it and breaking it. So shorter members are always good. Of course, there are some disadvantages too, like more pins and stress concentration and so many other things that we have to talk about. But again, I don't want to get into that. Now, in 3D trusses, again, the number of members and joints are related, this time through this formula, m equals 3j minus 6. And if you look at here, in this 3D truss, I have basically 4 joints. So 3 times 4, 12 minus 6, I should have 6 members, and you see I have, right? That's 1, 2, 3, and then that is 4, 5, and 6. So you see that it is working. Now in 2D, they are simple pivots that are connecting them. In 3D, they are spherical joints. Okay, which is the 3D version of pivot. So these are how we connect them to have simple two force members, and we can do easily thrust analysis either by, as we'll see next, by the joint method or by the section method. Okay, so keep that in mind. Now, moving on, by the way, the pictures or these problems are all taken from the engineering mechanics book by Bedford and Fowler, which is my reference. So these pictures do not belong to me. The credit goes to the 2 authors. So going back here, let's look at 2 different ways that we use to analyze trusses. And by analyzing, again, mean finding the forces within each member in general. Now, sometimes we don't need all of the members. We just need a few members. That's where we use section method. Sometimes we use joint method to find all of them, or again, some of them. So in the joint method, where the goal is typically to find the forces of all members, what you do is you have to first find the external support reactions. To do that, you take the whole truss, the entire truss, off of the support. So let's say this is a simple support, right? Here you can see there is a pivot and there is a roller here. So you take it off and then you show the free body diagram of it. So all the external forces is 400, 800. At the roller, we have 1 vertical reaction. At the pivot, you have 1 horizontal, 1 vertical reaction. And before you do anything else, the goal is to first find these 3 unknown reactions. Then you go joint by joint. Okay, so let's go ahead and do that in this case. So the goal is to find AX, AY, and E. How many external reactions can we find on any truss? Well, in 2D, remember, we have only three equations, some fx0, some fy0, some moment about 1.0. So we can at most have three reactions. So if this guy was also a pinned and not a basically a roller, then you have another reaction here. You have four, you only have three equations. That would be a statically indeterminate. Okay, so in a truss, you do not want to have ideally more than three reactions, and you want to have this portion a little bit easy to move to the left and right if possible, so it does not add extra stress in the members due to thermal expansion or contraction, if you can. That's a separate story, and talking about that is a separate story, whether you have to leave it as a roller or basically pin it down or something. So let's talk about this statically determinate thing. And in general, when would you say a truss is statically indeterminate? When you cannot find all of the unknown reactions, external reactions, plus all of the forces in the members. If you cannot, through static equations, equilibrium, find all of the unknowns, which are again the external reactions, which we show by R, and all of the forces in the members, which we show by M, if you cannot find all of them, we say this truss is statically indeterminate. In that case, we cannot either find some of these external reactions or some of the force in the members. Now, for a 2D truss, when is it that it's statically indeterminate? When this equation holds. M plus R is bigger than 2J, because these are the total number of unknowns that you have, M plus R, and how many equations would you get? Remember, in general, you have J joints. So 2J is all of the equations that you can possibly get, because each joint, if you separate each joint and look at each separate joint like this, okay, then there are only two equations that you can write, some fx0, some fy0. There is no dimension really here. It's all about a single joint. So you only have two equations. So 2J is all of the equations that you have. And these are all of the unknowns that you have. So if the unknowns bigger than equations, of course, it's statically indeterminate. If they are equal, then it's perfectly statically determinate. And if it's less than that, then the truss is not stable. Means that if you apply any force on it, the truss starts to move. And it's not stable. It cannot hold this position. Imagine you are moving on a bridge and the bridge starts moving. The joints start moving. And that is going to be a ride in a in a theme park rather than driving on a stable bridge. So these are the equations that you have for 3D trusses. The same equation applies, except it's going to be M plus R is bigger than 3J equal and less than 3J. Why 3? Because each joint in 3D, if you separate it, there are three equilibrium equations. Some Fx, some Fy, some Fz equals 0. So you have 3J equations. So your equations are going to go like that. So if I look at this truss, in this case, is this truss here on the left, is that statically determinate or indeterminate or unstable or stable? Well, we have to count it. And if you remember here, for this guy, we have M equals 7. And we have 3 unknown reactions. And we had 5 joints. So 7 plus 3 is equal to 10, not bigger, not less. So this truss is perfectly statically determinate. But again, as I said, if you pin this down, then you will get 11 as opposed to 10, and that would be statically indeterminate. Similarly, in this 3D guy, if you look at it, you have 3 rollers, so there are only 3 unknown reactions here, here, and here. So R is 3. The number of joints, if you remember, is 4. And M, remember, you have 6 members. Correct? So you have 6 members here, right? There are 3 up, 3 down, 6 members. There are 4 joints, and there are only 3 vertical reactions. Now, would that work? Really, is that statically stable? Well, if you look at it, 6 plus 3 is 9, that is 12. So this side is less than this side. That means if you just have it on 3 rollers like that, this is not a stable truss. Why not? Because yes, if this force that is applied from outside is just vertical, yes, it is going to hold. But if you have slight force in the either z direction or the x direction, none of this external reaction can stop the truss from moving in the z or x direction. So there is nothing, no support for x or z motion. So this guy is going to start moving. So this truss, the way it is shown, is really unstable. Yeah, right now, because the force is y, all reactions y, everything is good. But again, if you add more forces in x or z direction on any of the joints, the truss starts to move, and that will not be static anymore. That will be unstable. Okay? So you see that how we can have different scenarios here. Okay, now with that in mind, let's go ahead and look at this different methods for truss analysis. As I said, the first method, called joint method, we first draw the FBD of the entire truss and find the support reaction. So here we take it off. We go after finding AX, AY, and E. And remember, we can really only have 3 unknowns because we have one FBD here. Once we have them, then we go joint after joint. So let's go ahead and calculate that. So how much would you get for AX, AY, and E? So clearly, if you write some of the forces in the x direction for that FBD, there is no force in the x direction other than AX, so AX has to be 0. Okay, done. That's very easy. Then you have to take some of the moments about one point to get either AY or E, and then some of the force in the y direction. Now, which point would you use to take moment about? The point that has the maximum unknowns at it. Right now, since AX is 0, then it doesn't matter whether you do it about E or A, because only one of them, only they have one unknown reaction. So it's up to you. So here, maybe I take some of the moments about point O, and I go counterclockwise positive. And if you look at it, well, AY passes through A, so that has no moment. There are only 3 forces that create a moment about A, and those are these guys. This 400 is clearly creating clockwise moment, so that's going to be negative 400 times the distance for it is this 1 meter. That's the basically distance between the point, the normal distance between the point and the line of action of the force. So it is that 1 meter. And then the 800 is similar, negative 800, because that's clockwise. The distance for that is 1 plus 2, that is 3. And E is counterclockwise, so it's going to be positive E, and the distance for E is the entire distance, which is 4. That is equal to 0, and from here you should be able to find the E reaction, which if you do, you are going to get 700 Newton. AX was 0. E was 700, and then you say sum Fy equals 0, which in this case is AY plus E minus 400 minus 800. This is 0, and from here you should be calculating AY to be about 500, not about exactly 500 Newton. And you clearly see 500 plus 700 cancels 400 plus 800. Sum is 1200. And the moments are 0 as well. So there we go. We found the reactions. Now that we have the reactions, like here, a 500, a 700, and no x, it is time to go after joint by joint and find all of the internal forces of the members. Okay? Now the question is, which joint would you basically isolate from the rest of the world and look at this free body diagram? Which joint? Remember, at each joint you only have 2 equations of equilibrium, some Fx0, some Fy0. So ideally, in any FBD that you open up, you should have no more than 2 unknowns. So only attack the joints first that only have 2 unknown reactions, 2 unknown members at them. So if I want to start, I would not start at B, because if I draw B, right, if I draw B, then guess what? B has 3 unknown reactions plus this external force of 400. So there will be this force in it that I don't know, this force in it that I don't know, and this force in it that I don't know. So if this one I call it F of or T of, doesn't matter. Let's just call it T to stay consistent. So if this is T of AB and this is T of BC, and this is tension in member CBD, T of BD, you see, if I start with that first, I only have two equations but three unknowns, and that is not possible to go after. Okay, but if I start with joint A, I only have TAB unknown and I only have TAC unknown, and two equations, two unknowns, I can find them. Now, once I have TAB, which means this one is taken care of, now I can go after joint B because now it only has two unknowns. One of them is already determined. Now I can go after B. Okay, so always start from the joint that only has two unknown reactions at them. Okay, so here we start with joint A and we go after joint A. So what do we have at joint A? We have two equations and two unknowns. These tensions are both unknown. Now, one question you might ask is, how do we know that the forces in these two members are tensile force, not compressive force? Because we just learned that the force could be tension or compression. So how do I know that the force in this member AB is not this way, right, inward, as opposed to outward? How do I know that? Well, we don't know. We just make an assumption. I mean, you can physically look at it and basically find them, but it does not really matter. Initially, assume a direction, whether compressive or tensile. It doesn't matter. If, when you solve the numbers, if the number turned out to be positive, that means your assumption for the direction of it was good. If after solving, the number that you find for that variable becomes negative, that means it was the wrong direction. You have to reverse the direction that you assume. Okay, so just take a direction, assume something, and go forward, and the sign of the solution will tell you whether your assumption was right or wrong. So here, what I will do is, I'll go with that joint A, and of course I have two equations for equilibrium. Some force in the x direction, you see that is TAC, and then plus TAB times cosine of 60 degrees. That should be equal to 0, and then sum Fy equals 500, and then plus TAB times sine of 60. That is equal to 0. So two equations and two unknowns. Clearly you solve the bottom one first. Why? Because it has only one unknown in it, TAB. So from here you should be able to go after TAB. And of course you can see that, remember, sine of 60 is square root 3 over 2. And if you take it to the other side, you clearly see that is negative. So TAB is going to be negative 577 Newton. You see, you end up with a negative number. What does that mean? It means TAB was not actually tension. It was negative. TAB should be in this direction. And when it's negative, we say this member is under what? Member AB is under compression. So a negative solution means, since you already assume positive and it's negative, that means it is under compression. Then you plug it into the top one. So you plug this right up here and then solve for TAC. And if you solve for TAC, you are going to get positive 289 Newton. What does positive mean? Since you assume positive and it is positive, means this member is actually correct. The assumption of it is under tension. So this member is actually this way, that member is like that. There we go. So I found two of these unknowns. So far, these two members are determined. How many more to go? 5 more to go, right? 1, 2, 3, 4, and 5. Now, which joint would you attack? It's up to you. Now you can either go after E because E has 2 unknowns, or you can go after B because B has 3, but one of them is taken care of. Okay, or could you go after C? No. Why? Because C still has 3 unknowns. Could you go after D? No, because it has 3 unknowns. So once you take care of A, you can either go after B or E. You cannot go to C or D right now because they have more unknowns that you can solve. So the next joint I will go after is E. So this is E. There is a 700 here, and I assume two unknowns, and I assume both of them are under tension again. So this one is T of DE. This angle should also be 60 degrees. And this guy is T of basically CE. Right? And the analysis is very, very similar. So if you write it, so here I wrote the equations. If you solve, again, you're going to see TDE is going to be negative. And if I round it to a full number, it is going to be 808 Newton negative. Then again, I have to plug it right up here, and I can find T of CE. Now here, the negative, when it goes there, that whole thing becomes positive. And you take that to the other side, that also becomes positive. So ideally, TCE should be positive number. And it's going to be positive 404 Newton. There we go. So we found two extra unknowns. So now this one and this one are also taken care of. And now look into any other joints, B, D, or C. They all have two unknowns in them. So it doesn't matter which one you go next. And so now I look at joint D, and joint D has these three reactions where only CD and BD are unknown. ED is already calculated. I can use it. And these are the equations of equilibrium along Y and along X. And again, remember, anytime you have TED, now you can simply replace it by negative 808. You might also say, since this is negative, can I go and reverse this direction and use positive 808? The answer is yes, you can do that. If you reverse the direction and change the sign, you can also do it that way. So you don't need to mess up with negative numbers, but it should not be any problem for anybody. So the bottom equation clearly can give you TCD, right? So let's go ahead and calculate T of CD here and then plug it into the top one to get TBD. So this is going to be negative 116 Newton. Again, negative means that is under compression. So now we plug here negative 116. That should give us T of BD. That should be negative 346 Newton. One thing you can always do is to do a sanity check and make sure that the signs of these numbers that you got are correct. So if we look at this, it says that in reality, if you want to look at joint D, joint D here has all three numbers negative. What does that mean? It means you have to reverse all of these three. Would that do it? So if I have these like that, would that do it? And remember the numbers. If I do that, this is going to be 808. This is going to be basically 116, and this is going to be 346. Okay, clearly 808 and 116 together, their sign components should be able to cancel 800, so that does make sense. And then 346 plus 116 cosine 60 should be able to cancel 808 cosine 60, because this is bigger than those two. This one is going to be projected added to that. This one is going to be projected. So just half of that. So this is going to be like 404. Half of that is going to be like 58. 58 plus that 346 is going to be 404. So you see they cancel each other, and so equilibrium exists. So all of the numbers that we got are correct. So now we got this one and this one. And finally, now we can go after one extra joint, which is joint B. Let me do that last one. So this is joint B. It has TAB and TDB already figured out. You see that's TB, that is TAB here, right? So we have all of those numbers figured out. And so the only unknown at this is the CB. Everything else is known. And so this is the joint, and of course there is this external force of 400. So here is the joint, and now you can see that I can either use X or Y. It doesn't really make any difference in this case, and I rather use the X equation because it doesn't have this extra 400 in it. So that's what you have here. Sum of the force X is equal to 0, and again TAB is given, and T of dB is also given, so negative 346, and that means I can calculate that T of CB here. That is going to be negative 177 Newton. Done. Now I have all truss members, all the forces are calculated, therefore my truss analysis is over because I have all the reactions and all the forces. And I could do that because it was a statically determinate. Now you clearly can see that this is a time-consuming process because you have to find so many unknown reactions, right? And forces, M plus R of them. So if you looked at my channel, under the statics playlist, one of the things that I made for you is this application that I made in MATLAB called Truss Analyzer. And I really recommend you watch this video. Last year I did it as a gift for the new year. And what I did was basically I published this, so you can, it's a GUI, you can basically define the location of the nodes, the load on the nodes, which nodes are connected to which, what are the degrees of freedom of the node, basically determining what kind of support you have at each node, whether the node is free, whether there is a pivot, a roller, or anything on it. And then this so far is just for statics, this 4. The last 2 are to do stress in the members too, so it can provide their cross section and the Young modulus, so it can calculate the stress in them as well as their displacement. So it plots the original truss and the deformed version of the truss. It shows all of the forces in the axial members and all of the unknown support reactions. So these 2 blue windows are basically everything that you want to get. You provide all of those, so you click on these buttons, you provide all of those. If you don't know which format you have to use, you can click on this get help. You just check that item, do a check mark and do get help. It shows you what format to use. You click on solve, it shows all of the forces, it shows the truss and the deformed version of it. And if the deformation is small, you can move this slider to the right side to make the deformation larger and see it as a magnified scale, so you can see the deformation better. Okay, so this is a perfectly functional truss analyzer, and it works for both 2D and 3D trusses. Okay, so this is really good thing. I recommend you take a look at that, and it helps you with calculating all of these things. So you don't need to use ANSYS or anything else. You can just use this simple thing. It's really great. So this is the joint method. I applied it to a 2D truss, but you can do it on a 3D truss. For example, let's say this is the truss that you want to look at. And in this case, again, there are only 3 reactions that you have at points B, C, and D. Again, this is not a stable truss, but if you just want to solve, you can, because you have more equations than unknowns. So the only thing is here, it's not simple, okay? So here you have 3 reactions, and you can get up to 6 reactions, right? If you look at the FBD of this. And so in order to find B, C, and D, you have one equation, which is summation of forces in the y direction. So that is going to be B plus C plus D minus 1200. That is equal to 0, but that's one equation and 3 unknowns. You need to get 2 extra equations, and the X and Z sum forces cannot be used because there is no X force or no Z force. So the only 2 other equations you can use are the moment equations. So you have to take moment about 2 of these points. So I can take it about B, C, or D. So let's say sum of the moments about point B is 0. And here, You cannot go clockwise or counterclockwise because it's 3D, so you have to use the general formula for moment, which is arm vector cross the force vector. So in this case, for this force 1200, if I want to calculate the moment, I need to have this vector here, right? This R vector, if whatever you want to call it, RAB or R of A slash B. So that force should be crossed at 1200. And then the BC force, this vector here, R of C slash B, this vector should be crossed with the C, and then this vector here, which is R of D slash B, should be crossed with the D force, and sum of that is equal to 0. Now when you do that, your C force, when you want to write it as a vector, because here you have to say what? You have to, let me show one of them to you. So you say R of A slash B cross that 1200 force. Now what is that 1200 force as a vector format? So it is basically negative 1200 in the J direction. You see? And then plus R of C slash B cross what? The force at C is just C in the J direction. That C is an unknown. Plus R of D slash B cross and then D in the J direction. This is equal to vector 0. Now, those vectors are going to be so many I, so many J, so many Ks. But when you cross them with the J, only the I and the K component of it will have a cross with the J. The J component of it, J cross J, will be 0. Okay, so in this case, if I say what is R of A slash B, it's connecting B to A. B is at 0, 0, 0, is at 5, 3, 2. So that vector is 5I plus 3J plus 2K. Now, when you do that cross with negative 1200, the J component doesn't do anything, the I does and the K does. Okay? And the same thing for RCB and RDB, right? These vectors, which like RBD, this one is just going to be 10 in the I direction because it goes from 0, 0, 0 to 10, 0, 0. And this R of CB here, which goes from 0, 0, 0 to 6, 0, 6, this is going to be 6I plus 6K. That one will be crossed with C. Okay, so here you get one equation, and basically if you expand that, let me just continue here. If you expand that, it is going to be like 2400 minus 6ci plus negative 6000 plus 6c plus 10d times k, the whole thing equals vector 0. Move a little bit. As I said, there is no j because j cross j is not going to give you anything. So now the two vectors are equal. That means this coefficient is 0 and this coefficient is 0. Now that coefficient 0 means c is 400 positive Newton. Plug it here, and you can get d, and d is going to be 360. Now here the unit is not Newton, actually it is in feet for this problem, because so the forces should also be pounds, not Newton. So your LBF. So you got C and D, and now you plug in C and D here, and that should give you also B. And if you solve for B, you're going to get positive 440 pounds. There we go. And clearly, if you add these three numbers together, clearly you see some of it is 1200. So that should cancel that 1200, and the moment should also be 0. Okay, so here with one moment equation and one some force y equation, that's enough to get you all of the 3 unknown reactions. You don't need to take moments about C or D. They are also automatically going to be 0. So now that you got the reactions, it is time to go over joint by joint. So if I just go ahead and put these numbers here, so this guy was 440, and then this guy was 360, and this guy was 400. Now you can go over each one of the joints, and you have 4 joints. But which one do you start first? Remember, each joint has only 3 equations, sum fx, sum fy, sum fz0. So you have to only go after a joint that has 3 unknowns. Now, in this case, all 3 of them have 3 unknowns. All 4 of them have 3 unknowns. So it doesn't matter really where you start. You can start at any of them. But remember, you only had 6 unknowns in this case. So if you look at joint A, for example, you can find this member, and this member. If you go after B, that one is known, then you can go after these 2. And if you go after C, then everything is known except for this one, and you're going to find that. But when you do that, each joint will look something like this. Okay? And when you write the equations for it, you have to use unit vectors here, right? Because this TAD, TBD, and TCD, their magnitudes are unknown, but their directions, the unit vectors, are known. So if you want to write, let's say, sum of the forces, in this case, equals 0, it is going to be 360J, that is your reaction force, plus what? TAD magnitude, whatever it is that I don't know, along the unit vector of line A to D, along unit vector of A slash D, plus T of BD along unit vector of B with respect to D, plus T of CD times unit vector of C with respect to D. This is equal vector 0. Now, these 3 magnitudes are unknown. Seems like I made a mistake here. These 3 guys are unknown, but the unit vectors are known. For instance, U of AD is what? It's the vector AD divided by the magnitude of it. So what is that? Vector that goes A with respect to D. It goes from D to A. You have to find it. So this vector A with respect to D, what vector is that? That is end x minus initial x of 5 minus 10 is negative 5. 3 minus 0, 2 minus 0. So it's this. And so here, this is going to be, that's negative. So it's going to be negative 5i plus 3j plus 2k divided by its magnitude, which is negative 5 squared plus 3 squared plus 2 squared. Right? So you have to calculate all of that, and you have to find all of these unit vectors, and then this one is going to give you 3 equations, some iz 0, some jz 0, some kz 0. So you get 3 equations, and of course you have 3 unknowns in it. And you are going to find all 3 unknowns. But you have to calculate all of these unit vectors, these guys. These unit vectors have to be calculated. Once you have the unit vectors, then life is going to be easy. But you see that clearly calculating 3D trusses, it takes a little bit more computation, because now you have to be calculating a bunch of unit vectors and performing a bunch of cross products. So it takes more time, but the joint method still can solve your entire problem regardless. Okay, so I guess we are good about the joint method, and we can apply it to a 2D or 3D truss. The last thing we want to talk about is the section method. So the section method, which is the second method of calculating forces inside trusses, and it's easier to apply to 2D trusses than 3D, is when you don't look to find all of the unknown reactions in the members or the forces. You only want a few of them, one of them, two of them. Let's say in this same truss that we just solved, I don't want to know all of these members. All I want is member BC. What is the tension or compression in member BC? Then, instead of finding the external reactions, which you have to do first anyways, and then going over each and every one of these members and each and every one of the joints, you cut the truss such that this member of interest is basically broken into two parts. So some cut like this or any other cut, okay? So you could cut something like this, for instance, make the top part and the bottom part, or left part and the right part. And then the member of interest should be exposed, should be cut, so we can look at the internal force of it. And the way you cut, you should make sure that the number of unknown reactions, the number of cuts, the number of members that are cut with their unknown reactions, it's such that you can find them, especially the one that you care about. I mean, look at this. If I cut the way I did, I have generated 3 unknown reactions here. And when you do that, by the way, you have to either look at the left side of the cut or the right side of the cut. Or if you do like this, you can look at the top part or the bottom part. Okay, you look at one of the 2 generated pieces. So now I cut it like this, and I have these 3 unknowns. Can I find all 3? Yes, because I have 3 equations of equilibrium, xy, some fx, some fy, and some moment about the point, and you have dimensions here, you have angles. So guess what? I can find all 3 of them. Okay? So yes, definitely in this cut I can do it. And not only that, another reason this cut is really good is if I know this external reaction, which as I said, you have to find it in the first place. If you look, do I need all three equations to find this unknown of interest? The answer is no. So let's say some moment about A. Do I need all 3 of them? No. Why? Because if I look, these 2 other unknowns are horizontal. They don't contribute anything to the sum Fy. The only one that has any y component is this guy and these 2 known values. So all I need is just sum Fy. That's enough to give me TBC. So with one cut and one equation, I can determine TBC. Just that beautifully. And better than that, do I need to find all of these 3 reactions? The answer is, again, guess what? No, because I cut it in half. All I care about is this external reaction. Whatever this one is, who cares? I'm not looking at the right side. I'm looking at the left side, so I just need to know that 500. So when I want to solve this and find the reaction in member BC, how do I approach it? First, as I said, you have to find you have to determine a cut that cuts the member, and do not, in this case, generate more than 3 unknowns because you don't have more than 3 equations. Ideally, you can only solve the unknown with one of those equilibrium equations. That's like perfect scenario if you can. If not, you know at least from 3 equations, 3 unknowns, you can do it. The other thing is, from the unknown reactions on the supports, you only go for the one that you like. So in this case, sum fx is, of course, 0. So this member AX, this reaction AX is clearly 0. Now, between AY and E, all I want to find is, since I'm looking at the left side, I only care about AY. So what do I do? First, I take some of the moments about E to find AY. And remember, we just did that. And that means when you do that, it gives you that AY of 500. We just did it above. So once I have that, and now I look at this left side, as I said, now I say sum Fy equals 0. And sum Fy in this case is 500 minus 400, and then minus TBC times sine of 60 degrees. And guess what? That is enough to give me TBC. Right? Which is basically 100 times 2. So 200 divided by square root 3, which is the same as what you found up there. Okay? So you see 2 equations and I get what I want. Now you might say, what if I cut it like this? So if I do that, then I will be getting something like this. Look. So I have one reaction here, and then, yeah, that was a little bit too long, but then I get another reaction here, and then another reaction here, correct? So I have 4 unknown reactions, as well as this 400 and 800. And the good thing is I don't need to find the external reactions because I'm looking at the top part, so that is good. But the problem is I have 4 unknowns here, and 4 unknowns and 3 equations you cannot solve. Now, can I find this one from a subset of the ones that I want? Well, is that a possibility? If I write some fx, all 4 of these unknowns will show up. If I write some fy, again, all 4 of them will show up. So fx and fy are no. One equation, 4 unknowns. That's not going to work. You consider both of them again. That's not going to work. Okay? Now, if you take a moment about any critical point, would that do it? Well, if I take moment about here, of course, this is going to be eliminated. So that is not a good point. So you have to go with this. If you take some of the moments about that, then these 2 will show up. So although this one is in it, but this one is also in it. So that is not going to work. And you might say, what if you look at the bottom portion of that? If you look at the bottom portion, would that be any different? So if you look at the bottom portion, then you will have this. First of all, you have to find these 2 external reactions, but let's say we did 500 and 700. Again, you see there are 4 unknown reactions. And this is the one that you care about. And again, if you take moment about any of these 2 points, that will vanish. If you take moment about here, again, both of those guys will show up. So there is no way that you can solve it by a horizontal cut. You have to do a vertical cut. And you have to make sure that vertical cut cuts this member. Now, the way when you cut this member, right, you might say, can I cut something like this? Well, you can. But again, remember that by cutting that, you are bringing in how many members? You are cutting 4 members. And remember, you only have 3 equations. So it's better to cut such that you cut minimum number of members, including the one that you like, not just a random cut. And this needs a little bit experience and engineering intuition to do the best cut and to get exactly what you want. Okay? Now, as a second practice, I want you to look at this other example. Here we want these 2 horizontal forces, and these are all F to FF. So clearly, if you find the external forces, this X force has to be 0, clearly, because there is no X force. And then since this is a symmetric design and symmetric loading, clearly each one of them will be 2 Fs. Correct? Because the total load is 4F. So these are the external reactions. Now, how do you go about those 2 members? Now, you might do several different cuts, so you find them one at a time. Or somebody might say, well, that's kind of obvious. These 2 can be cut by something like this. If I cut that, what would you get? Well, what you would get is this, basically. Look. So you get a 2F here, and you have already cut 4 members. So this is one of them, this is one, this is one, and this is one. Good. And of course, 1F here. And remember, the one that you want are these 2, not these 2 diagonal ones. So is there anything that you can do? Well, guess what? If I, in this case, take a moment about this point C, which 2 forces will show up in it? Or 3 forces? This one does, this one does, these 2 will vanish, this F passes through, it will vanish, and this external one. So some moment about C will bring in these 2 unknowns in it. So let's do it, and let's do counterclockwise positive. So that 2f is negative, so that's going to be negative 2f, and the distance is L. And then this force here, T of dg, and this guy is T of BE. Both of them, their distances are L and L, if you can see here. The top one is clockwise, the bottom one is counterclockwise, so it's going to be negative TDGL positive TBEL. This is 0, so one equation and two unknowns. And now if you look, these two have X forces only, and these two, if you look at them, they have X and Y forces. So if I write the X equation, these two will come in, which I don't want them to come in because I have 4 unknowns. If I write Y forces, then the unknowns will not be coming in. So you see here that cut give me one good equation, which has only 2 unknowns in it. That's not a bad equation. But the rest of this FBD is not going to give me what I needed to get. Okay? That is obvious, right? That cut is not going to get me what I want in one equation. I mean, one equation gave me a lot of that, but not all of it. So is there any other cut or any other thing that you can do? And you might say, well, instead of having a cut that cuts both of them at the same time, how about I have a cut that only cuts one of them? Like what? Like something like this. If I do that cut, what do I get? If I do that cut, then I will get this force here and this force. And then what? A force there, as well as this force here, this external one. So that guy is 2F. This one is the one that I care about, and these 2 extra ones that I don't care about. Good? Yep. Now, what do I do? If I do some Fx, then these 2 will come in, and this brings in an extra unknown that I don't want. If I do some Fy, this one that I care about does not come in. If I do some moment about point A, then this one again comes in as well as this one, which I don't want, but there is a better point here, and that is this point here, this point B. If I do take moment about B, both of these other unknowns that I don't care about will vanish. Only 2F stays, and this force here, which you call it T of basically dg. So here I do some moment about B in this cut. And clearly you have a negative 2F times L, and then positive, negative, another negative, sorry, negative, because that is also clockwise, negative TDG, and that is times 2L, right? This is 0, and clearly you can see that TDG is negative F. You see, one equation, one unknown. Perfect. I got that. Now I can plug it up here. And I can get rid of the L's. So you see that TBE is what? That is going to be a 2F, and then positive dg, which is minus F, so that is going to be positive F. You see, so one of them is negative F, the other one is positive F. Okay? And they are not equal, of course, because about the horizontal axis, the mid-axis, this thing is not symmetric. Okay, I can say these two are equal because it's symmetric, but these top one and bottom one are clearly not, and these are the results. So you can use more than one section to get what you need. And this is how you use the section method. Okay, so this video got a little bit long, but I guess I covered all I needed to cover for you to do proper truss analysis. and I told you about this very good resource that you can have. Hopefully you enjoyed the video, and I'm gonna see you in the next lecture. Thank you.